Hello everyone. Today I'll talk about small noise approximation for Bayesian optimal experimental design with nuisance uncertainty. My coworkers are Luis Espat and Raul Tempone. So when we talk about experimental design, what we mean is that data Y is modeled by a deterministic forward map G and random noise epsilon. It is the goal of the experiment to learn about parameters of interest theta, and since measuring data is typically very expensive, we need to make sure that the experiment is designed in such a way that data is very informative. We also consider nuisance parameters phi that contribute to the overall uncertainty of the model, but should not factor into the search for the optimal design. Finally, we consider several repetitions under consistent setup. It follows immediately from the data model that the likelihood is given by a normal distribution centered around the forward model predictions with covariance equal to the noise covariance. The expected information gain quantifies how much we learn about the parameters of interest. In this equation, we have outer integrals separated from inner integrals by a nonlinear function, in our case, the logarithm. We propose a novel small noise approximation for the inner integral over phi and an already established Laplace approximation for the integral about theta. For the small noise approximation, we use first order Taylor expansion, resulting in a normal approximation for the likelihood function with an updated covariance matrix. This update contains the gradient of our forward model with regard to the nuisance parameters and the nuisance covariance. We see here that if the nuisance covariance becomes large, the small noise approximation stops being applicable as the resulting updated covariance matrix is no longer positive definite. For the Laplace approximation, we employ second order Taylor expansion, resulting in a normal distribution of the posterior, where the mean is given by the maximum a posteriori estimate, and the covariance is the negative inverse Hessian of the log likelihood function. To showcase the effects of considering nuisance parameters, we present the following simple example with Gaussian priors for theta and phi. We can see here that in the case where both theta and phi are parameters of interest, although we have a higher overall expected information gain, the maximum design is different than if we consider phi to be nuisance parameters. And this results in more information about the parameters of interest theta. What we can see here is that if we introduce nuisance parameters and marginalize them with our proposed small noise approximation, we obtain no increase in computational cost. To showcase the practical applicability of our proposed method, we present an example from electrical impedance tomography, where we have composite laminate materials consisting of two orthotropic plies with a fiber structure, and it is assumed that electric current is conducted better along the direction of the fibers rather than transversal to it. So if we attach electrodes to the surface, we can inject electric current, measure the outputs, and thus recover the angle of the fibers and detect flaws in the material. We consider the exact conductivities of the materials to be unknown, and therefore nuisance parameters. The position of the electrodes is the design that we want to find. We can see here that the shift between inlet and outlet electrodes contributes much more to the expected information gain than the distance in between electrodes, and that we want to maximize both. If you want to learn more about this topic, you can find a preprint version of the work that this presentation is based on arXiv. And if you want to watch more detailed video presentation, you can follow this YouTube link. Thanks for watching.